Cisco's IDS module for routers. All right, well, we've talked about all of the IPS software configuration with signatures and alerts and so on. It's now time to focus on just some of the specifics of the hardware. Not all IPS appliances are appliances. Some of them may be a module inside of a router and a switch. For example, the one you're staring at on the screen right now is known as the NMC-IDS, the network module that allows you to run an IDS inside of your router. So this video is dedicated to the specifics of that device. We're going to talk about how everything connects. What differences does it have when it comes to the packet processing? Does it do anything different? I mean, how does it handle, for instance, VPNs terminating on the router or access lists that are on the router? And then we'll finally look at the unique commands to the NMC-IDS, because there are a few commands that we have on this that we do not have on appliances, primarily to handle, for instance, you don't see any power switch on there, so you have to reboot it, and we'll talk about how to access it and so on. So the NMC-IDS module is the piece that Cisco has created for their routers to allow them to run the IPS 5.x software. This is the same software we've been talking about this entire series, so you're not going to see too much difference. The reason that we have this is just to discuss the differences when you're working with a router. Most mainstream Cisco routers that this can be installed in, but I should add recent on there. When I think of mainstream Cisco routers, for some reason I still think the original 2600 series, which has been around for quite some time. This does not work in the original 2600 series. It works on the 2600 XM, which is the enhancement Cisco created a few years back, but that one's already been discontinued too. They're trying to replace everything with their new ISR routers. So I'll just rattle off a list of the mainstream Cisco routers I'm talking about. You got the 2600 XM, 2691, 3660, 3725, 3745, and then all of the ISRs that support a network slot that big. And ISR stands for Integrated Service Router. Those are the newer line of routers that have the VPN functionality and the beautiful GUI, and they're really shiny and silver. Now it does say that this module right here has a completely separate processor. It's got its own hard drive, it's got its own software, but it does add a little bit of load to the router because the router has to make a copy of every packet that it receives and send it also across the backplane. You can see that on the third bullet, across the PCI backplane to this module. So pretty much you can just imagine, the flow of traffic coming in just being carbon copied to the sensor. So it will add a little load, and it does have to have the Cisco Express Forwarding switching turned on, or CEF. Just about every router comes with that nowadays. You just go to global config mode and type in IPsef to support that. Because the IDS sensor is inside of the router, we have some unique challenges that we don't have when we had the separate appliance sitting on another device. We have things like, for instance, access control lists. Does the sensor process things before them or after them? Or what if you have a VPN? I mean, does it just fly right through, or does the router terminate that, unencrypt it? How does all that work is the big question. So what I want to do is take these one at a time, and the big strategy that I would use, at least, or that I did use when I was thinking about this, is think about this sensor as being kind of in the middle of the router. It's, I tried to draw it sort of coming down right here, but it's just sitting in the middle of the router. It's not sitting before an interface. It's not sitting after interface. It's in the squishy Oreo center. So the ACLs, access control lists, if an inbound access control list is denying traffic from coming in, for instance, you've got, see my little packet, inbound ACL, does that get processed by the sensor? No, wham, drops off. The sensor never sees that. So inbound ACLs that block traffic will prevent it from ever being seen by the sensor, and that's usually a good thing. Outbound access control lists, one that's headed out this way, here's my packet, passes out, goes through. Did the sensor see it? If the outbound one denies or permits it, that's not the question. It passed through the squishy middle of the router. The sensor had a chance to look at that and monitor that. So outbound access control lists do not prevent the sensors from seeing that. Inbound does, outbound does not. Let me jump down to VPNs because that's a quick one to explain, and then I'll hit the NAT explanations. VPNs can either terminate or pass through a router. It all depends on your architecture. Sometimes people have the VPN terminate at a Windows server behind it or a VPN concentrator behind the router. And if it is passing through the router, the sensor can't see it because it's encrypted. Well, I shouldn't make that broad statement. The sensor can see the stuff that's not encrypted, meaning the layer 2, the layer 3 header, but everything else from layer 4 and above is all jumbled up and scrambled, so the sensor will not see those things if it's passing through the router. Now, if it's terminating at the router, imagine the internet being over here on the right-hand side. If a VPN terminates at the router, it terminates right there on the outside interface. Now, is that before the squishy center? Absolutely. So if you terminate the VPN at the router, the sensor inside of it will have no problem inspecting each one of those packets fully. So ACLs, VPNs, we've got that. That makes sense. Now let's move on to the NAT. NAT can be one of the most confusing topics for people, not because of the technology. It's actually fairly simple in translating addresses. It's all about the terminology. And it makes it especially tough because Cisco has actually moved NAT down to the CCNA level program. And those poor people are just, they have to learn the inside local, inside global, outside local, all those terms. Well, we're not going to get into all of that here. It's not going to get too deep, but we will see inside and outside NAT. Now, 95% of the time, you will see people use inside NAT. And what that means is you have a inside address over here. We've got our source address. It's a private address, 172.16.1.10. And they're going to a destination of 4.2.2.2, which is some internet valid address. Now that just happens to be, here's your tip of the day, public DNS server. That's actually one that I use all the time when I'm out at a client site, and we don't have a DNS server to use. So if this source is trying to access this destination and we're translating it out, that's known as inside NAT. You're translating something from the inside to the outside, or vice versa, from the outside to the inside. Now that's what confuses most people, is they go, well, wait a sec, vice versa? How is inside NAT vice versa? How is outside to the inside also inside NAT? Well, the perspective that you have to think of this is you are making an inside host reachable on the internet. To describe outside NAT is kind of tricky, but outside NAT allows you to have a outside address redefined on the inside network and translated over here. I'll give you an example of that in a second. Let me first off focus on inside NAT. So inside NAT says this is where we start and that is where we end. As we go out, the source address is translated from something that's private here over to something that's public and valid on the internet, and when the response comes back, it's translating it back through. So why all this discussion? Well, we come back to the question of what does the sensor see? A lot of its detection mechanisms, it needs to see, certain IP addresses. Well, again, remember it's in the squishy middle of the router. I would tell you to remember that inside NAT translations happen, let me fix that real quick. They all happen right here. Right there on that outside interface. So it comes in with the source 172.16 going to this destination. Life is good, life is good. Aha, we're seeing the sensor. And then wham, as we leave this interface, we're translated to the public IP address going to that destination. Likewise, when we come back, we come in and we're immediately translated on that outside interface back to the private. So we go from 8.21.56.1 over to 172.16.1.10. Aha, seen by the sensor, and then back to the client. So the question of what does the sensor see? The client or the sensor sees on inside NAT translation the pre-translated addresses. The world is doing NAT. The sensor will see the private address going to the public address, and when the response comes back, it'll be the public address going to the after translated private addresses. Now, when it comes to the outside NAT world, we are now changing the focus of what address we are looking to translate. Inside NAT says we want to translate some private address right here to a public address over here. Or vice versa, a public address over here to a private address over here. It's the inside address translation. Outside NAT says we want to translate the destination address. So maybe, here's the scenario. Maybe there is no 4.2.2.2. Maybe there is only some other address out in the world that is 5.5.5.5. But for whatever reason, maybe we've got some servers hard-coded to point to that address. Maybe our clients are used to going to that. Maybe DNS records are pointing to that. Whatever the case may be, we want to translate whenever somebody on the inside accesses 4.2.2.2, we want to translate that through the router and have it finally go to 5.5.5.5. So again, the same concept applies when you're configuring outside NAT, and I'm reaching for my pen here. When you're configuring outside NAT, think of the translation as happening right there. So this one comes in, it says, hey, I want to access, 4.2.2.2. It comes into the router says, oh, okay, 4.2.2.2 hits the squishy middle. What's the sensor see? It sees source, destination. So it sees those two addresses, comes out here, translates right at the outside interface, and now is going to a destination of 5.5.5.5. Did the sensor see that? No. It only saw 4.2.2.2. Likewise, when this server out on the internet responds and comes back, it's going to come back and say, hey, this 172.16.1.10 comes into the router, translates right there on that outside interface back to 4.2.2.2, passes through the squishy middle. What does the sensor see? Still destinate or a source at this point of 4.2.2.2 and a destination of 172.16.1.10. So on the return traffic, it still does not see the translated addresses. So I could, I guess, make the global statement of when we're thinking NAT, just think of it happening on that outside interface. The sensor only sees the pre-NAT addresses. Outside of those special functions, the sensor inside of the router works just like a sensor. Oh, I suppose there is one more difference. The appliance sensors, when you plug them into a switch, will receive ARP packets because ARPs are broadcast, they go everywhere. But if you have the module inside of the router actually interprets the ARPs and does not forward them onto the module. So this sensor does not do analysis on ARP packets. Likewise, the router also has a lot of built-in functions that keep just bad packets from getting through. For instance, something where the options in the IP header are all goofed up, or something where the version is wrong on the IP information in the header. I mean, these are obviously bad packets. The router will grab them and drop them and not even forward them onto the sensor. Whereas an inline sensor or appliance sensor plugged into a switch might get those. So overall, you can just globalize that and say the router filters out some junk before it will get to that module, but otherwise, everything else is analyzed. Oh yeah, we're on a new slide here. Let's talk about setting up the NMC IDS. This is from start to finish what we need to do to get this thing up and running in a router. Number one, you have to plug it in. That is an absolute mandatory thing. You've got to pull off the cellophane wrapper. You get that nice, the cellophane smell. It's great. You take it, you plug it into the router, and it is now chugging away. When you do that, and I should also mention, power off most routers. Most of them, I say, because the upper end routers like the 3660, 3745, and the 3800 series allow you to do hot swap. So you could pull that module out while it's active, though not recommended. But the other ones, you have to power them off. So you plug it in. You connect the management port to the network. And what I mean by management port, let me see if I can grab an image real quick. There we go. This is the module. This port right up front is the management port. Now the actual sensor interfaces are on the backplane of the router. It uses the fast Ethernet interfaces or serial interfaces on your router as its own. So the management port is going to be where it communicates with the management workstation. That's going to be this one right here. Now if they happen to be in the same room, which is pretty rare, you can use a crossover cable. But otherwise, just go ahead and slam that thing into a switch with a straight through Ethernet cable. So you plug that in, you connect it. when you power the router back up, or if you're using one of the hot swap, it will automatically show up as a new interface. If you do a show running config, you'll see interface and you'll see IDS sensor, module, and port number. So it might be 1/0 or 2/0, depending on what model of router you're using. But do a show running config, make sure it's showing up there, because if it's not, you've got a problem. Also, last thing before we get into the config, make sure you disable the iOS-based IPS. A lot of the newer routers, the 2800 series, 3800, and 1800 series, all come with this built-in iOS-based IPS. It's pretty much software-based IPS. It's good, it works well, but it does cause a lot more load on your router. This module is pretty much, it's like, you could think of it like a hardware RAID controller versus allowing Windows to do your RAID between your hard drives. So if you are running the software-based IPS, disable that, because it will conflict with the one that you are installing and cause a lot more processor overhead. The next step in this game is going to be to assign the new IDS sensor interface an IP address. And you can see right on there, it says it is best if this is not a valid network address, because otherwise you open the IDS sensor itself to potential attack. So the best strategy is to use a loopback IP address instead to allow that sensor to operate correctly. So here I have my my iOS simulator right here. This is as good as it gets when we come to simulation technology. I'm sitting on my router. Imagine I have a router with a network module installed. I'm in global configuration mode. I'm just going to type in interface, loopback, and we'll just say I'm using loopback 0. Wham! Look at that. You see that simulated technology? You can't beat it. You can't beat it. I'm going to give it an IP address. IP address, and I'll just say this is going to be 1.1.1.1 with a mask of 255.255.255.255. Not many people know that. You can do that. You can give a 32-bit mask to that, which means it will just be a single IP address on a loopback interface. So, oh, look at that. Simulated technology kicks in. I'm going to exit back out of that interface configuration mode. And this is a bug we're fixing in our simulator. There we go. We're back in global configuration mode. And what I can do from this point is jump under the new IDS interface. So say I had that module installed in a 2600 XM router. It would be interface, and I would type in IDS sensor 1/0, module 1, port 0 on there. I hit enter, and I'm now in the interface configuration mode again, and I just give it the IP address, IP unnumbered, and it will relate directly to loopback 0. Hit enter, and now that sensor will be pulling its IP address from loopback 0. Now while we're here, I'll exit back out of this interface configuration mode and type in a command that is default on just about every router running a modern iOS, but just to make sure you catch it, go back to global config mode and type in IPsef, which turns on the Cisco Express forwarding capabilities of the router, which is required to run the IDS sensor. Now what I've done there is I have given the sensor an IP address that is not really accessible from anywhere except this router. So if I knew about it, I could, for instance, point a route to this router and access it. So for instance, if I'm on my management workstation, I can point directly to this and access this interface, or I could telnet to the router and get to that interface. But that IP address wouldn't be accessible for most people sitting on the network. It would be pretty much you could think of it as a quasi-private IP address just for your sensor interface. Now remember that when you are configuring that sensor interface, it is just an interface. So it will be shut down by default, and you may have to issue that no shutdown in there. Now we come to the third part of setting the clock on the network module. This I know it sounds simple, but this is actually a really big piece. And remember, the clock is essential to your IDS because that's going to be what it marks all of its alerts with. So when you're trying to track something and figure out what time something happened, you're going to need to know the clock is accurate. So we have a few options when we're setting the clock on the module. We can either use the clock of the router, or we can use NTP, the Network Time Protocol. The module does not have its own clock. That's something to keep in mind. It either has to get its time from the router or using NTP. So Cisco recommends right off the bat use NTP. And the reason for that is because the module by default uses Greenwich Mean Time, GMT time zone, which may or may not be accurate compared to your router's time zone. And then we throw in there the fact that most of the world, not Arizona, that's where I am, but most of the world has to adjust for daylight savings time. So if you set the clock via the router and it seems like everything's fine, well, daylight savings time rolls around and all of a sudden what the router is. So it can get really confusing because you have to set the time zone and summer daylight time settings accurately on the module and on the router. So that is why Cisco recommends that you always use the network time protocol for both the module and the router if you can do it. If NTP is not an option, the second best option is to use NTP for the router and then allow the module to use the router's time as its clock. And if NTP is completely out of the picture, then you're going to have to just resort to using your best guess on the router for the time and allowing the module to set itself from there. But the clock is definitely a big one. From there, we're nearing the end here. The last major step that we have in setting up the NMC IDS is to turn on packet monitoring on the interface. This is the command, you can see it on the screen, IDS service module monitoring, that we need to type under each interface that we want to funnel its traffic into the sensor. By default, the sensor is now running. It has an IP address. Life seems to be good, but it's not watching your interfaces. So if your router has fast Ethernet 0/0 and fast Ethernet 0/1, and you want it to monitor those two interfaces as packets pass through, you need to get under each one of those interfaces. We need a router sim here. Router config, type in interface fast Ethernet 0/0, and then type this command, IDS service module monitoring. Immediately, your router begins making copies of all the packets that are going through that interface and sending them to the sensor for analysis. So at that point, your sensor will be set up and it will be monitoring traffic, but you may still want to access it to do, say, some configuration. The way that you do that is one of two. We can go onto our router and type in, this is the easiest way, service module IDS sensor, our module and port number, and hit session. Doing that first command in here is like establishing a console connection to your module. You can reboot it and stay connected. It's just like being plugged into the console port. You could also telnet to the sensor if you wanted to. And the way you do that is actually something known as reverse telnet. Now I know many of you have gone through the CCNP track and you know what reverse telnet is all about. But if you haven't, let me just describe it for you. Telnet allows you to access a device. Reverse telnet is pretty much telnetting into a device that telnets to something within itself. Reversing the telnet. It's used a lot of times since an octal cable plugged into a router that allows you to access the console port of many different devices. It's also used a lot of times to configure modems that are plugged into routers. So you can't access the modem directly, so you have to do a reverse telnet from the router to the modem. The way we do it to reach the sensor is we type in telnet, a router IP address. And this could be any router IP address. It could be assigned to its fast Ethernet, its serial port, it doesn't matter. It's just so the router knows you are accessing something on the router. You could be accessing the router or something else. That's why we followed up with a port number. Now here's the tricky part. The port number, when you're doing a reverse telnet, is always 2000 something. That indicates to the router that you are doing a reverse telnet. In this case, the sensor is always the first line number of the module that you're accessing. Now I know you're probably thinking, say that again. I know many of you probably just rewound right there. It's the first line number of the module that you're accessing. Now the iOS automatically reserves 32 numbers for each module. 32 line numbers. So you could actually have 32 reverse telnet sessions, if you will, on each module, theoretically speaking. This is the first one. So I have a formula for you. The way to figure out what port number to type in there is just to take 32 let me grab my pen here, 32 times the port number plus, and go ahead and add in there, 2001. That adds our 2000. So for instance, if we had the module installed in port 1 of our 2600XM, we would say, okay, port 1, 32 times that is 32 plus 2001, so that'd be 2033. Oh, I just put 2000. 2033. So I would actually telnet to the router's IP address space 2033 as a port number. If we had it installed in port 2, that would end up being 2 times 32, so it'd be 64 plus 2001. So we would telnet, if the module was in port 2, to 2065. That would allow us to go directly to the sensor. Say we're sitting at our workstation, we telnet to the sensor directly by putting that port number rather than having to telnet to the router and enter that command up top, service module, to get there. So that's how we can reach it via telnet. Now finally, we reach the maintenance commands, and this is the last piece of uniqueness to that module. We have some maintenance commands for that module on the router. Since this is a module and not a separate appliance, we don't really have an on-off switch for it. So what we can do is we can type in service module, IDS sensor, our module and port number, using the syntax we have here, followed by ... That's one of these arguments. Reload is considered a soft reload. It'd be like typing reload on your appliance software to where it tries to shut everything down and reboot gracefully. Reset is your hardcore pull the plug sort of reset. This is a dangerous one to do because it's just as if you literally pulled the plug on that module. Remember, it's running its own operating system on top of Linux. It's the same thing as your appliance. So this would be as hard as you can reset the thing. Only use the reset if everything's frozen, meaning maybe the Linux kernel crashed or something like that. It'd be something very desperate because there is a risk that you can corrupt the hard drive and have to reload the software if you do this reset. The session we've already seen, that's actually the command you see up top here. That allows you to access it as if you were connected to the console port. Shutdown does a graceful shutdown of the module. This is most likely if you plan on removing it. Maybe you have one of those hot swap routers or you plan on powering your router off. You don't want to risk damaging the Linux kernel by just doing a hard power off. You can shut down the module first. And finally, status just gives you the status of that module, and you want to see when you type that command that it's in the steady state. That will let you know that everything is operational, but it will just give you a flyby report of the health of the module. Oh, one more thing. If you shut down the module but don't pop and you want to turn it back on, you can just reset it at that point. Like I said, it's like the power switch for your module. All right, well, let's go ahead and wrap things up. Those were the specifics on the NMC IDS, how we can control that module inside of our router. So we talked about how everything connects. This plugs right directly into the backplane of the router, into that PCI backplane. It doesn't really have any physical interfaces other than the management interface that's plugged into the front, allowing us to have some sort of management workstation that connects. We then talked about the differences in packet processing, how we can process the packets on this when we have NAT enabled, how we can process when access control lists are enabled, how, which packets are sent to this versus an appliance-based system. And then finally, we talked about the unique commands to the NMC IDS, primarily the commands that allow you to reboot this thing, to shut it down, to access it using the service module session syntax. All of these things directly related to the fact that this installs into the router rather than being a separate